Hey guys, welcome back to some more A-level further maths revision. This video we're taking a look at some further stats 1, and we're taking a look at a second video in exam revision. So you're looking for some revision for your exams. Hopefully this will help. So let's take a look at these questions. They're all past paper questions from the old spec mainly, but a couple from basically the new papers. So the first question here, just a nice brief one just to get us started. Explain what we understand by the central limit theorem. So central limit theorem is something you need to know for further stats 1. This is only on the A level, so you're doing the AS. This doesn't matter too much, but the A level, this is definitely important. So what is the central limit theorem? Well, the central limit theorem states that if we take, let's say, a random sample here, so let's just say take x1, x2, all the way up to say xn, okay? This is going to be a random sample. So it's a random sample of length n. And we normally say n is large, okay, where n is large. Well, what do we obtain here? Well, if this is drawn from any distribution, doesn't matter what distribution we take this from. So this is drawn from, I should say, the population okay, so it doesn't matter if it's Poisson, if it's a uniform distribution, doesn't matter. This is the magic of the central limit theorem. Okay, so it's drawn from the population of any distribution, and let's say the mean is just mu. So it has mean mu, and then let's just say it has a variance of sigma squared. Then we can approximate this as a normal distribution. Okay, so how would we write that? Well, in this case, then x bar is a normal distribution with a mean of mu. Now, our standard deviation is our original variance, and we divide it by the sample size n. Okay, and that's the magic there, that very last line. So it doesn't matter what your distribution is. If you take a sample from it, a random sample of length n, typically n is large, we can approximate this as a normal distribution, a Gaussian distribution. Okay, so that's just question 1 there, 3 marks for that. Hopefully not too bad, but make sure you do understand how the central limit theorem works. You can be asked to explain it, so it's just worth remembering the basic steps there. So that's question 1, just a nice one to get us started. Let's take a look at now, something a bit more mathematically involved. So this is question 6 here, taken from the old S1 papers. And here we've got our probability function, okay? So the probability that bx is equal to little x is given as 2 parts. We have a bracket 3 minus x, for x being 0, 1 and 2, I don't really need that comma there, and it's b if x equals 3. Okay, so we've got the table given as below. So when x is 0, that's 3a. And why is that the case? Well, if you substitute 0 into here, notice this is only true when x is 0, 1 or 2. So if x is 0, this would be 3 minus 0, which is 3, times by a, so we get 3a. Works again the exact same for 1. So if x is 1, that's 3 minus 1, which is 2, times by a, we get 2a. So finally, if x is 2, so if x is 2, this is a times 3 minus 2, which just leaves us with a. Okay, a times 1 is just a. So in that case, that value there, so we can just put that in ourselves, that's a there. So that's just the first part, asking us to complete the table. Part B then, we're given that the expectation of x, in other words the mean of this distribution, that probability function, is equal to 1.6. Okay, so this is 1.6. I want to find the value of a and the value of b. So for this, the first thing I'm going to do here is if we're told that the expectation of x equals 1.6, what I'm going to do is work out the expectation of x using our table here across on this side. So let's work out the expectation here. Obviously this is going to be in terms of a and b, but what we'll do is we'll set that equal to 1.6 because that's what we've been given. And what we can also do is we can use the fact that the sum of this probability here must be equal to 1. Okay, for any probability function, all the events will add up to 1. So let's start by doing that. So the expectation of x, well, that would just simply be x times the respective probability. So the first one is going to be 0 times 3a, which will obviously be 0, but we'll write it down for clarity. Then we're going to add 1 times 2a, which will be 2a, but we'll do that in a second. Then we've got 2 times a, and we'll finally have 3 times b. So let's work out each one of these individually. So that's 0, this is 2a, that's 2a, and finally that's 3b. But we know all of this is equal to 1.6. So in that case, if we do it over here, 4a plus 3b is equal to 1.6. Okay. Now let's use the fact that the sum of these probabilities here must be equal to 1. So in that case, 3a plus 2a plus a plus b is equal to 1. So if we simplify this, 3a plus 2a is 5a plus another a. So we get 6a plus b is equal to 1. So essentially what I've got here now is a simultaneous equation. I've got 6a plus b equals 1. I've also got 4a plus 3b is equal to 1.6. So it's completely up to you how you prefer to solve this now, whether you use substitution or elimination. I'm going to use substitution here. So I'm going to rearrange this. So if I call this equation 1 here, call that equation 2. I'm going to rearrange equation 1 to be b equals 1 minus 6a. Okay. And then what I'm going to do is I'm going to substitute this now into equation 2. So I've got 4a plus 3b, so 3 lots of this. And we know this equation is equal to 1.6. So all I need to do now is expand this and then just solve for it, because that's what we've done. We've eliminated b using substitution. So I get 4a, 3 times 1 is 3. 3 times minus 6a is minus 18a. And this is equal to 1.6. So I get 3 minus 14a equal to 1.6. And just rearranging this here, I'm going to take this minus 14a across the other side, make it positive. I'm going to subtract 1.6 off both sides here. So I get 14a is equal to 1.4. So in that case, a is 1.4 divided by 14, which would clearly just be 0.1. Okay, so a is 0.1. And then finally b is really easy to work out. So if we use that, b is equal to 1 minus 6a, and a is 0.1, then this is just simply 1 minus 6 times 0.1, which is 0.6, which gives us 0.4 there for b. Okay, so b is 0.4 and a is 0.1, if that's not too clear. Got that from down here. Okay, and there we go. So that's our answers there. So that's 6 marks in total. Hopefully not too bad there. So that's question 2 done. Let's take a look at another one. So this one, quite a short one. Just testing this key idea of using probability Poisson distribution even. This is also the wrong paper. This is an S2 paper. I always get something wrong. And what year was this? I've got it written down somewhere. So this was June 2006. So June 2006. Okay, so apologies for that. S2 there. So we've got an estate agent who sells properties at a mean rate of 7 per week. So the first part just asks us to suggest a suitable model, aka what distribution are we using, and 2 reasons basically to support that model. So I've already actually said what this is, but if you're not too sure how to tell, the key is in the language of the question. So if we just highlight the important part here, where it mentions about this per week part here, this is very, very important. If you're dealing with a distribution and we're talking in essence of per week, per month, per day, per hour, per time frame, then it's a Poisson. Okay, so that indicates to me Poisson distribution. Okay, so we're going to use Poisson for this. Obviously, you're doing further stats 1. Poisson is kind of the main distribution that you taught, so it's probably going to come up at some point in your exam. So obviously, you've got a big idea where it's coming. So for part A, the model I'm going to use here is a Poisson distribution. What I'm going to do first is just define the variable that I'm using. So I'm going to use x here. So x is a Poisson distribution. The lambda value here is just the mean. So we've got a mean rate of 7 per week. So lambda is 7 there. And then let's just define x, where x represents the number of properties sold in a week. It's worth mentioning that obviously I don't have to use this x as my variable. I could use y, I could use z. You can use whatever you want. Obviously, just make sure it's clear here what x or whatever variable you use does represent. Okay. 2 reasons that support this. So in other words, they're asking you for 2 assumptions that support this being a Poisson. So the first one I'm going to mention is that the sales of the houses would occur independently. Okay, so sales occur independently, and then another point that we can make is that they occur at a constant rate. Okay, so sales occur at a constant rate there. Part B then, now we're just working out a probability for this. So we want to find the probability that in any random chosen week, the estate agent sells exactly 5 properties. So what we're asked to find here is using this same distribution, so it's just per week. So we're using x, again, is a Poisson distribution with mean 7. We're asked to find the probability that x equals 5. Okay, so it's important that we check that we've got the right time frame. So because it's asking for a chosen week, this is fine. If it said for maybe a 2-week period, then you would need to scale our mean by 2. We times it by 2 to match that. Okay, but because it's just per week, this is fine for now. Probability x equals 5. 2 ways of doing this. You can use the formula to calculate a probability for a Poisson distribution, or you can just use your calculator. And I would say just use your calculator. You'll need a graphical calculator to do this. So if I type everything that I've put in my calculator, so I've gone through distribution, so the dis button, then it's a Poisson, and then you'll either have the choice of PPD or PCD. Now because this is exactly 5, we're going to use PPD. Okay, if it was say less than 5, it would be PCD. So all you need to do now is input the right parameters. So our mean is just what we've been given in the question, the mean rate. So in that case, mu is equal to 7. And your x is just the value that you want given here. So we want the probability that x equals 5. So we put x equals 5 into there. And if you press equals now, or enter, whatever it is on your calculator, your probability here should be 0.1277. Obviously make sure this is for a variable, not a list, because that's the other option you can do. Obviously we're only doing this for one value. So there you go. So that's the probability you should get there, 0.1277. Again, you could use the formula. Either way is fine, but the calculator is much, much quicker. And in the interest of saving yourself time, that's the way I'd recommend. So again, a nice easy question there. 5 marks, hopefully not too bad. Now let's take a look at a bit of a trickier one here. This question's on probability generating functions. These can be quite tricky. And like you see, this question's quite long, 12 marks in total. So it might take a bit of time. So what I'd recommend, if you're not too confident with these, have a go first, pause the video, and then have a go, see what you do, and then watch through this, see if you can get the same answer. So hopefully you paused it. Let's have a go at it together now. So the first part, we want to show that k is equal to 1 over 36. So how do we do that? Well, this part 8 is very common. Hopefully this part's not too bad. If you want to show that k is equal to 1 over 36, we need to consider for a probability generating function such as the one we've been given. We know if we substitute t equals 1 in, then this full expression should be equal to 1. Okay, so substituting 1 in instead of t, what we then get is that the full expression is equal to 1. Okay, so if I do that, I've got k, 3, so wherever there's a t, I'll replace it with 1, so that's 1, and I've got 2 times 1 squared, so that's going to be 2. We square all of that, and we know that all of that is equal to 1. So all I need to do is actually work out this bracket now, so 3 plus 1 is 4, plus 1 over 2 is 6, so this is k times 6 squared is equal to 1, so that's 36k is equal to 1, so then finally k is simply 1 divided by 36. Okay, so part A, quite standard, that does come up quite regularly, so make sure you can do something like that. Part B, we want to find the probability that x is equal to 3. So when you're finding a probability of a probability generating function, what we need to do is consider the function that we've got. So if I just quickly clear what I've got so far. So our probability generating function is given here in the question. Now for this generating function, the probability that x is equal to 3 is given is the coefficient I can't spell, might be wrong, of t cubed. Okay, so it's the coefficient of t cubed. So if the coefficient of t cubed is, say, 1 over 2, then the probability that x equals 3 is a half. It's 1 over 2 as well. So what we're going to have to do here is expand until we've got the t cubed, and then once we've got t cubed, look at the coefficient, question done. So if we expand this here, I just need to expand this part. Expand these two brackets here, and then we'll times the coefficient of t cubed by 1 over 36. Because don't forget we've got the k on the outside, right at the front here. So I'll just put it in just so we don't forget it. So expanding this, I'll just go term by term. So 3 times 3 is 9. 3 times t is 3t. 3 times 2t squared, that would be 6t squared. Okay, so that's okay so far. Now we're going to go along with this one. So t times 3, that would be 3t. Where's my pen gone? So that would be 3t there. We've got then t times t, so that would be t squared. And then finally t times 2t squared, that would be 2t cubed. Okay, so that's a t cubed there, so that's what we're going to need. Let's just underline that for now. And then finally, expanding this last term here, so 2t squared times 3, so that's 6t squared. 2t squared times t, so that's 2t cubed. Again, we need that, so we'll underline it. And we don't really need the last one, but we'll just do it for the sake of completion here. 2t squared times 2t squared, 4t to the 4. Okay, so the only ones we're bothered about is anything with a t cubed, which is just these two. So if we add these together, I get 4t cubed. And then don't forget we need to times this by 1 over 36. Okay, so even if you can't do part A, you still can carry on with the rest of the question. Okay, so don't be put off if you find maybe the first part difficult. You still can carry on with this question. Now obviously I only care about this 4 here, the coefficient of t cubed, so I get 4 over 36, which is equal, dividing top and bottom by 4, so 1 over 9. Okay, so 1 over 9 there. So the probability that x is equal to 3 is just simply 1 over 9. So that's part B. And then let's take a look at part C. So this is 8 marks. Bit of work for this one. Let's have a go with it. So, oops, I don't want to do that. I can't see which one is it. There we go. So part C, let's have a go at this. So we need to show that the variance of x equals 29 over 18. So I've included this at the bottom here. This is given in your formula book, so I'm not including anything extra that you don't have. They do give you the formula for the variance. So for the variance, you're going to need the expectation of basically the probability generating function. So to do that, we're going to differentiate it. We also need the variance, which requires the second derivative. So make sure you're somewhat confident with your differentiation here. Usually the differentiation is nothing further than product rule and chain rule. So it shouldn't be too bad, but let's take a look at it. So if we calculate the first derivative then, what would that be? Well, for this one, it'd just be chain rule, right? You can either use chain rule or you can use the full expanded form that we've just done and do that term by term. It's completely up to you. I'm just going to use chain rule for the sake of speeding it up. So, straight away, the 2 as the power would come to the front. That would be 2k. And we just times by the derivative of the bracket. So what's the derivative of the bracket? Well, there's a t there, so that's a 1. And then the 2t squared will be 4t. I'm going to times 2k by 1 plus 4t. And then we times all of this here by our original expression, 3 plus t plus 2t squared. But hopefully this part shouldn't be too bad, just standard differentiation, which you should be confident with through A level. Okay, so that's just the first part of that. Oops, I made a mistake. I can't do it myself. Don't forget to take one off your power. So there we go, I nearly made a mistake myself. So that's the first derivative there. All we need to do now is actually work out the expectation, and the expectation is given by substituting t equals 1. Okay, so we substitute 1 into here. What will we get? So it'll be 2k, which we actually know what that is, because k is 1 over 36. I've got 1 plus 4t, so that would be 5. This part here, this is 3 plus 1, which is 4, plus number 2, so that's 6. Okay, so it's going to be 30 times 2k. In other words, that's 60k. And so that's 60 over 36, which gives us, what does that simplify to? So that'd be 30 over 18. I think that's 5 over 3, right? Yeah, 5 over 3. So that's the expectation of x. Now we need to calculate the second derivative. So this one's a little bit trickier. So g prime prime t. So just calculating the derivative of this. Now this would be product rule. So if I calculate, so if I write that as 2k bracket 1 plus 4t times by this, and then differentiate using product rule. So what I get here is this one times the derivative of this plus this times the derivative of this. So just standard application of product rule here. So what would that be? So that'd be 2k 1 plus 4t. And then we're going to times it by the derivative of this, which would be 1 plus 4t. Okay, so times by 1 plus 4t. So that's the first part. And then all we do is we add on this part times by the derivative of this. So just writing that first bit out. Then we times it by the derivative of this. Sorry, this part here. And what would that be? Well, that would just simply be, in this case, 8k. So that'd be 8k. Which, what we can do here is factor out a 2k. That's 2k. Square bracket 1 plus 4t squared. I've got 1 plus 4t times number 1 plus 4t here. Plus, I've got 4 lots here. If I factor out a 2k, I've got 4 lots of this. Okay, so that's our first part there. So at this point, hopefully, everything seems okay. So if I get my calculator ready, because I forgot to do one of the calculations myself. So all we need to do now is actually use this formula here. So the variance of x, we try that at the top here. is given as g prime prime of 1. So that's the only thing we need to do here. We need to just plug 1 into here. So what does that give us? That'll give us 49 over 18. So I have done that part. So you just plug 1 into here. In fact, I'll just do it just so we've got it as clarity. So that'd be 2k. So that'd be 5 squared plus 4. 3, 1, 6. So that's 4 times 6 there. So that's 25 plus 24. So that's 49 times 2 over 36. So what I get there is my 49 over 18. So yes, that works out perfect. So all we need to do now is just use the full formula. So g prime prime at 1 plus g prime at 1 minus g prime at 1 squared. Okay, so writing all this out in full, just so we've got it, that's going to be 49 over 18 minus 5 over 3. Oops, sorry, that should be plus 5 over 3. And then minus 25 over 9. So let me just quickly do this just to make sure. We should get 29 over 18. But I'll quickly do it just to make sure I've got the same here. Yeah, perfect. We get 29 over 18. And there we go. So that's exactly what we wanted to show. So we've shown that. I'm happy. Hopefully that makes sense. If there is anything that's unclear, like always, just leave a comment down below. And I'll try my best to explain it maybe a bit better. So let's take a look at the next one here. This is S3 June 2009. So we've got a sample of size 8, which is taken from a population that's normally distributed with a mean of 55 and a standard deviation of 3. I want to find the probability that the sample mean is greater than 57. So let's just write out what distribution we've got here. We've got a normal distribution, mean 55, and standard deviation 3. So if I write that as the variance, that's 3 squared. What I want to do here is find the probability that the sample mean is greater than 57. So in this case, we're going to have to use the central limit theorem. So using the central limit theorem. So what is the central limit theorem? Oh, and the central limit theorem gives us an approximation for a normal distribution with the mean given as it is here, 55, and then our new standard deviation here, our new variance I should say, is going to be the variance, so that's going to be 3 squared, which is 9, divided by the sample size, which is 8. Okay, so that's our approximation there. So in this case, all we actually need to do now is work out the new probability. So this new probability is going to be the probability that x bar is larger than 57. So it's up to you how you do this. You can just use your calculator now using these parameters here. That's fine. You can do it by hand if you want. I'll show the calculation by hand, but you can just use your calculator equally. This is the probability now that z is larger than. It's going to be 57. The thing that we want to test out is greater than, minus our mean 55. And I'm going to divide this by the square root of 9 over 8. This will give us the probability of z being larger than 1.885, 6, so on, so on, and so on. And if you work this out, this is 0.0294 there. Okay, so this is obviously just your standard formula to calculate a probability for the normal distribution. That should hopefully be okay from your A-level stats. This is just the application here for the central limit theorem. So again, make sure you're confident with the central limit theorem and how you obtain your new parameters there. But that's just it. So that's my probability here. Question done. Quite a nice quick one there for 5 marks. The next question is another long one. We've got a chi-squared question here. So we're testing for an association, and that association is between cholesterol level and the intake of saturated fats. So for any hypothesis test, a nice way to start is by actually stating the hypotheses. So if we do that, let's do it here. Stating the hypotheses. So we've got a H0 and a H1. The H0 is always that there is no association. So there is no association we should really state the association between the two things. So in this case, we're testing for an association between cholesterol level and the intake of saturated fat. I'm just going to abbreviate that as SF, okay, for saturated fats. And then H1, I'm not going to write it all down. The only difference is for H1 that we're testing that there is an association. So there is an association. With everything else just being the same, so between cholesterol and intake of saturated fats. Okay, so the H1 is just the exact same, the only difference being that we're testing now for an association. So that's our H0, our H1. What we need to do first is calculate any expected values. So, expected values here. Well, what I'm going to do is I'll write the row and column totals. So 12 plus 8, that's 20 there. 26 plus 54. So that would be 80 there. 12 plus 26, so that's 38. So if I just quickly write all this down, change my pen colour here, so we've got it. So that's 38. And then finally 8 plus 54 gives us 62 there. Okay, so we've got our row and column totals. So that's the first thing I'd do for a question like this. Now we're going to work at the expected values. So how do we work out the expected values? Well, to work at the expected values, all we do is, like we've just done, the row and column totals. And what we do now, so let's just say we wanted the expected value here for high. So that would correspond to this 12 here. So what would that expected value be? Well, it's just going to be the row total, so 20, times by the column total, which is 38, so it's going to be 20, times by 38, and then we're going to divide it by the sample size. So the doctor takes a random sample of 100 patients, so we divide that by 100. Okay, put that into your calculator, and what you get there is 7.6. Okay, so that's that expected value. Obviously, we need to do this 3 more times for all 4 possible values. So that's the next one will be 20 times by 62 and divide that by 100. So this corresponds to, let me narrate it here. So this corresponds to this one here now. That's the one I want to work out. So we use that row total of 20, we times it by the column total 62, divide it by 100, and we get 12.4. So now working at the bottom left, it's going to be 38 times 80 divided by 100. That'll be 30.4. And now finally working at the last one, 80 times by 62 and divided by 100, which gives us 49.6 there. Okay, so we've got our 4 expected values. So once you've got your expected values, we can now go on to actually working out the test statistic. So to do that, we use this formula here. So we're going to sum the observed minus the expected squared. And then we're going to divide it by the expected. Okay. So, for example, the first one would be, say, 12, because that's what we observed. So 12 minus the expected, 7.6. We're going to square that value, and then we divide it by the expected. So we expected 7.6. We divide it by 7.6. If you calculate all of that, you'll get 2.547368, so on and so on. And then obviously we need to do this for the next value and the next value and the next value. So we'll have 4 values in total. So the next one would be, say, 8. That's what we observed. So that would be 8 minus 12.4. Square this, and we divide it by 12.4. Okay. If you calculate this, what you're going to get here is 1.5 0.61290. Okay. Now, I'm not going to work out the next two individually. I'll just write them down on the screen here. So I've got this one so far. We've got this one. We also need to add these two values as well. So your next value will be 0.6368421 plus 0.3903225. If you add all them together, what we get here is 5.136 there. Okay, so that's our test statistic. So we've only got a few more things left to work out here, and the question's actually done. So what else have we got to work out? Well, we need to work out the degrees of freedom and the critical value. So the degrees of freedom here is really easy. So we use V to represent the degrees of freedom. So we look at how many rows we've got. We've got 2, and we minus 1 off. So that's 2 minus 1. And then we times this by the columns. How many columns have we got? Again, we've got 2, and we minus 1 off. So in other words, this is just 1 times 1, 1 squared, which just gives us 1. So we've got 1 degree of freedom here. And finally, all we need is our chi-squared value. So we're looking for the chi-squared value with 1 degree of freedom, and our significance level is 5%. Okay, just using your formula book here to get this value, you should get 3.841. Okay, so if I just quickly rub this bit out here, just so we've got through. All we need to do is give our conclusion now. So what we do is we compare our test statistic, this value here, to our critical value. So 5.136 is larger than 3.841. So in that case, we reject H naught. We reject if this value, our test statistic, is larger than our critical value. So reject H naught. What we say then is that there is an association. And I'm more than likely going to run out of room to do this. So basically, I'm just going to abbreviate this. So there is an association between capital C, which is cholesterol, and intake of SF. So saturated fats there. Okay, and that's our conclusion here. So 10 marks for that. Like you can see, there is a lot of individual working out, but overall, I wouldn't say that question is too difficult compared to, say, maybe a probability generating function question. Hopefully that doesn't seem too bad. So there we go. So let's move on to the very final question here for this video. Hopefully quite a nice one to finish with here. We have a hypothesis testing question. So the bacteria are randomly distributed in a river at a rate of 5 per litre of water. So straight away, the distribution should be kind of jumping out at you now. If you can't recognise the distribution, again, take a look at the language. The fact that it's a rate of 5 per litre of water, we're going to use a Poisson here. So Poisson distribution. Okay, so let's just note that down, Poisson distribution. So again, for any hypothesis test, let's start by just defining the hypotheses. So this is H0 and H1, and like we said, this is a Poisson distribution, so our parameter is lambda. Okay, so the first one's always equals. For now, let's just leave this inequality here. Let's see what we're going to actually test for. So we're taking a sample of 0.5 litres of water from the river. We find that it contains 7 bacteria. So we're testing at the 5% level of significance whether there is evidence that the level of pollution has increased. So if I want to test whether it's increased, then in this case, we're going to use greater than here. Now there's actually 2 values you can give for what we test in here. I'm going to pick 5 as my value here. But you can, if you want, pick 2.5. And the reason for that is because you're using the sample here as 0.5 litres of water. So obviously if you divide your litre of water by 2, you get half a litre. And in that case, you divide the rate, which is 5 by 2, to get 2.5. That is absolutely acceptable as well. But I'm just going to pick 5 here, given that's the first one I've been given. In this case then, if we're using half a litre of water, then my Poisson distribution is the mean rate divided by 2, which is 2.5. Okay, so just like we were knowing before. The only thing left to do here now is actually compare our evidence to a critical value that we're going to work out, or to the 5% I should say. So what do I test for here? Well, we take the probability that x, this is variable here, with it being greater than here, we copy that, so it's greater than or equal, and we compare this to the evidence. So this is 7. Okay, what we found is that it contains 7 bacteria, so we're testing this against greater than or equal to 7. So this would simply be 1 minus the probability that x is less than or equal to 6. And at this point here, now this is just a standard, plug it into your calculator and work it out. So this would be 1 minus 0.9858, which gives us 0.0142. And all we do now is we compare this to our 5% level of significance. So, compare this value. So because this is smaller, 0.0142 is smaller than our 5%, 0.05, in that case we reject H0. So therefore, reject H0. What we're saying here now then is that there is evidence at the 5% level of significance to suggest that pollution has increased. And there we go. Back on right. So pollution has increased. So there we have it. So that brings us to the end of this video. Like always, I hope this has helped. Any issues, anything that's unclear, just leave a comment down below. Cheers.